Now, just to be clear on what factoring means, it means to write the sum of 4 terms as a product. In any number of ways that can be done. It could be 2 factors, 3 factors, however many factors, but the goal is to write this as some kind of product. Now, I would be the guy back in high school that said, hey, this doesn't factor. It sure doesn't look like it. There's no greatest common factor. It doesn't look like any algebraic identity I've ever seen. But indeed, it turns out to factor. Now, we're going to use these marvelous little tools called elementary symmetric polynomials. Now, this subscript here actually means it's the sum of all the distinct variables. This 2 means it's the sum of the pairs of distinct variables. And this means it's just the sum of all 3 variables. And there's only one way you can do that. And so this is called sigma 1, sigma 2, sigma 3. Now, why do you think these are important? Well, if you were to expand this out like we do right down here, things like this come up when you start expanding this object out down here. Now, just to give you, there's a lot of moving parts right here, but take a look right down here. And I left out the tedium of the work here, but when you expand this out, you get this entire expression right here. Now, I'll get to why it looks like this, but this is a lot of work. This is 5 or 10 minutes of work just to expand this out. I just wrote down the result here. But notice that what happens here is you get this expression right here, all these combinations of x squared z, 2 variables raised to the second, raised to the linear power, But notice that's what happens when you actually multiply sigma 1 times sigma 2. Now, here's sigma 1. And again, this is a lot of work that got left out, but I don't want to clutter it up too much. This is sigma 1. If you multiply it against sigma 2, you actually get this expression right here. Now, notice you get 3xyz, a little bit of promise right there. That's part of this, right? So you get 3xyz, but notice just from a notational point of view, and again, I'm trying to decide how much to actually talk here, but this is the same as 3 times sigma 3, right? So you see that part of it is already an elementary symmetric polynomial, all right? Now, so again, just this piece right here is 3 sigma 3. This is your sigma 3 right over here, right? So that part is 3 sigma 3. But notice what happens right down here. Also, when you multiply this object out right here, you actually get all of this stuff right here. Okay, you get every bit of this with a little bit left over, it turns out. We have to make an adjustment for that. But notice what happens right here. We get that all of this, when you expand out x plus y plus z cubed, ends up being x cubed, y cubed, z cubed, plus 3. We get it in terms of these elementary symmetric polynomials, which will end up factoring for us, okay? Now, what happens here, we have, let's see, we have 6 of them here, okay? But we only have 3 of them here, so we have to make this adjustment right here. Okay, we have 6 times sigma 3 right here. And so we actually have to add a 3 sigma 3 right here to make this thing balance out. You guys can verify that. But notice right here that if you subtract all of this right here, if you subtract this circled object from this side, you end up getting this expression right here. Okay, so you see we have that the expression we're looking for. Okay, just that much. Now we still need to adjust for the minus 3 xyz right here, but we have that. Well, the object that we're trying to factor is actually equal to this. Okay, so let's go to the next screen and see if we can finish this thing off. Let me clear this out. Okay, and let's go to the next screen here. Okay, folks. Now, I just rewrote the problem, okay? But notice, and again, I hate it that it's this way, but let me just go back to the screen one more time. What I'm concerned with right here is this piece. See, if you take a look at what we did on this previous screen, okay, we got that x cubed plus y cubed plus z cubed is equal to this right here, right? Equal to this object right here. But we had not subtracted off the minus 3xyz, which is also 3 sigma sub 3. And so that's why on the next screen right here, we get this added object here. But notice it just cancels that one out. Okay, it just cancels that one out. And so we actually end up with this expression right here. And that's quite amazing, because notice that this does factor. See, that's cool, folks. So you see, we got this thing that looked like it was going to be difficult to factor, and we factored it in terms of the elementary symmetric polynomials. And notice that this factors very easily, right? Factors very easily. You can just factor out a sigma sub 1. And so this is the factored result using elementary symmetric polynomials, all right? But we don't actually know. Let's see, where did I write that down? Yeah. Okay, yeah, there we go. Okay, so you see, y'all, we do have this factored out in terms of sigma sub 1 and sigma 2. But notice that we don't know exactly what sigma 2 is at this stage of the game, right? So what we have to do is, and that's this work right here. And again, I probably should have let you guys just notice it, but what we have going on right here is this would be 2 times sigma 2, right? Okay, this part right here would be 2 times sigma 2. And so you would get that x squared plus y squared plus z squared, okay, is equal to this. If you subtract this from both sides, you get x squared plus y squared plus z squared equals to 2 sigma 2. Okay, and so that's what we used as our substitution on the next page. And again, sorry for not being able to keep it on the same screen. I just haven't quite figured out how to do that. And so that's what happened right here. This factored piece right here, remember, this is equal to sigma sub 1 is equal to x plus y plus z. So you see, that's what happened right here. Okay. See, it is factored in terms of the elementary symmetric polynomials, but we have to re-express it in terms of x, y, and z. Okay. So sigma 1 is actually equal to this parenthetical piece right here. Now this sigma 1 squared is, if you want to go back and look at that, that's all of this sigma 1 squared. Just think of it, that's x plus y plus z quantity squared. That's all of these terms right here. Okay. Hope y'all see that. It's really easier that I'm making a mess of it by just talking about it. But again, sigma 1, let me go ahead and show you what I'm saying here. This piece right here, and I'll come out over here. This is equal to x plus y plus z quantity squared. Now, y'all, again, that's something you have to do. It's a manual operation, and I don't want to clutter. But if you expand x plus y plus z quantity squared, it's not too hard to believe that you would get x squared plus y squared plus z squared plus 2xy plus 2yz plus 2xz. All right, and that's exactly, again, this circle object right here is exactly these 1, 2, 3, 4, 5, 6 terms, right? And again, 3 sigma 2 is even easier to see because sigma 2 is just xy, xz, and yz, right? So that's where this came from. All right. And so what do we got here? Did I just collect like terms, or is it good to go? Let's see. We got it, don't we? Look. Oh, yeah, y'all. There was a little bit of simplification that went on here, right, folks? This is 2xy, 2yz, 2xz minus 3 times all of that. So that's why we just have that much left right there. Okay. So in a manner of speaking, it was already factored here. It just wasn't simplified. But isn't that stunning? This object, what looks totally impossible to factor, actually factors nicely. So just briefly to recap what happened, we transformed it to the elementary symmetric polynomial domain. We factored it in the ESP, not extrasensory perception, but the elementary symmetric polynomial domain. We factored it in that domain, and it factored trivially, right? This is just a piece of cake, you know. Now, there were some difficult transformations kind of, you know, at the beginning, but once you get it to here, it's a trivial factorization. But we can't stop there. It's a transform, you know, not unlike, say, the Laplace transform. You do your work in one space and then convert it back to the other space, all right? So we did the work in this ESP space. All right, and then we had to substitute everything back in. And I hope you see how sigma 1 would be this piece right here. sigma 1 squared is this entire piece right here. That's sigma 1 squared right down here, right? Okay. And then minus 3 sigma 2, we end up with this object here. And then this very last line, we actually just collected the like terms for these last 1, 2, 3, 4, 5, 6. Y'all let me know what you think. I think it's tedious, but I don't know even how to approach the problem as a factorization problem directly without using some sort of substitution scheme. All right, thanks for listening.